At the end of the last video, we had this little example where we have a sinusoidal voltage defined as propagating the plus z direction. We gave you some characteristics, and the goal was to write it out in phasor form. For the sake of completeness, let's start out by writing it out in the time domain form, and then we'll do the conversion. Before we do that, let's write out the key parameters. So the first thing that we want to find is the frequency in units of radians per second, which is omega, and that is defined as 2 pi times the frequency, which was given here. And so we will write that in as 2 pi times 8 times 10 to the 6 hertz. And after that calculation, we will leave that, let's leave that as 16 pi 10 to the 6 radians per second. Now the other term, the other coefficient that we need to find is beta. And beta, remember, in the earlier slide we defined as omega divided by Vp, and conveniently the propagation velocity was already provided here. So using the omega that we just found, we have 16 pi times 10 to the 6 divided by the velocity, which is 2 pi times 10 to the 7th, which gives us 0.8. Now remember, the beta is multiplied by z, right? And the things inside the sinusoid should be unitless, so this beta coefficient should have a unit of 1 over length, so 1 over meters in this case. In the time domain, therefore, we can see that the voltage can be written as a sinusoid that looks like an amplitude of 10, as we were given here, times the cosine of the frequency omega t. Omega is 16 pi times 10 to the 6t, minus because we said that it was in the plus z direction, so they should have opposite signs, minus beta z. So beta we found as 0.8 times the variable z. Now we can rewrite this into the complex form, which is just using Euler's method. We can rewrite this as 10 e to the, let's do the z term first, so minus 0.8 z, as we see here, and then let's put this one in, so e to the j 16 pi times 10 to the 6t. So these two are the same. We've just used Euler's rule to write it out in complex form. Now to get phasor form, all we need to do is just neglect the frequency portion. So the phasor form is V of z is equal to 10 e to the minus j 0.8 z. And there we go. So now this is the voltage that we would use for our subsequent transmission line analysis. Now before we move on, let's do one more example where you're supposed to go back the other way. So say we did a lot of math and we found out that our final answer for whatever it was that we were looking for looks like this, where it's V of z, and notice that there's a 4j here, so it's not in just clear straight up polar form, so you have to convert that into just a clear polar form that's in the form of e to the j theta. And then convert that into the time domain sinusoid cosine of something with t and z in there to get the time domain answer. So why don't you work on that a little bit, and I will see you in the next video where we'll solve this.